Good afternoon, Mindsetters, and welcome to it. It's another beautiful edition of Mindset Learn Extra. My name is Katleho, and of course, we're going to be together for an entire hour with our teacher here, of course, grade 10s, doing nothing but physical sciences as usual. As I've told you, I'm not alone in the studio. Hey, ma'am, how are you?
I'm well, thanks, Katleho. It's good to be with you, Mindsetters. And today we're going to be tackling graphs of motion. Very, very, very important. And I know some of you are even starting to think about getting your driver's license or learner's licenses. And so it's really important to understand motion and what's happening with that.
Of course, so we're going to be doing motions today. I've got brilliant or cool competitions lined up for you. 3 just in fact, and you stand a chance, of course, to win a Casio calculator as usual. And I'm going to be introducing 2 more beautiful competitions as the show goes on. Remember to get in touch with us on Twitter. We are at Learn Extra with an X, and on Facebook, of course, it's www.facebook.com/Learn Extra with an X. That's where you can access all your notes and get in touch with us and more or less post all those questions for our teachers who will be ready and willing to answer you and make sure that you interact with us. So I'm going to just shoot straight and take it away to Tracy.
Thanks, Katleho. So, Mindsetters, as I said, graphs of motion. And graphs can sometimes be something challenging to interpret and to work with. And so it's very important that you spend a bit of time interpreting what is happening in a graph and understand the different graphs that we've got, specifically with graphs of motion. So, as we go through today, we're going to be looking at examining different types of graphs of motion. We will also be interpreting the graphs using the gradient and what we call the area under the graph to determine information about the object's motion. So we've got gradient and area under the graph, and those 2 tools can help us to get more information from just looking at the graph. And then always, Mindsetters, we love to solve problems. We love to tackle questions, exam type paper questions, very, very helpful. And there's lots on the go today. So I want to pose the challenge question to you. And always, we want you to go and do this challenge question, post your answer on our Facebook page, and make sure that you're interacting, because that's how you're going to learn. You can't just sit back with your feet up in the air and do nothing. You've got to really take this and really answer the questions. So the question says, a man runs from point A on a straight line along the track A, B, C, D, E, F, G. The velocity time graph. So he's going in a straight line, and we're marking out certain points along the line that we are numbering or labeling A, B, C to G. From that, we can monitor his velocity at those different points on this straight track. And we can take those values and plot them on the graph. And that's what we've done here. So the graph, it's a velocity time graph, and that's helpful. Below represents the motion of the man. And so we have this velocity versus time graph. Using information on the graph, calculate the acceleration of the man between different points, E and G, and the distance covered by the man in the 100 seconds. So that's 2 questions. I want you to go and tackle that from the graph. But you've got to have the notes. You've got to make sure that you've answering these questions, and you're going to be able to read off stuff from that graph. So go and take that challenge question and make that your own. Let's get into the summary. So when we speak about motion, there's different ways we can talk about motion, or you can describe motion. I could describe to you in words about a bicycle, a cyclist moving along, or a man running, or an object moving. So we can describe motion in words. We can describe motion with numbers. In terms of an equation, we can calculate motion. And the third way is we can use graphs. And graphs can really represent, they say a picture says 1,000 words. A graph can really represent a lot in terms of information. So there are 3 main types of motion graphs. And always, 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 I'm going to ask you to check out what are the labels on the axes. And usually time is on the bottom, but on the vertical axis, that can be different. So you could have a position versus time graph, or you could have a velocity on the y-axis, or an acceleration on the y-axis. All of those can be very valuable. And whenever you draw a sketch graph, because you often will be asked to actually go and represent or draw a motion type graph, you have to write in what is on the axes, both with labels and then with units as well. So watch out, labels on the axes. And we've mentioned a position versus time graph, a speed or velocity versus time graph. And remember, velocity is a speed, a value, a magnitude, I should say, with direction, because it's a vector quantity. And speed is just a scalar. And then acceleration versus time. So let's get into looking at some graphs. If I start with uniform motion, now by the word uniform, I'm meaning constant. Okay, where the motion is going at the same speed, probably, with the same velocity. So it's going to be covering equal distances in every unit of time. Because if you think about it, you wear a uniform to school, you all are dressed in the same way. And so uniform is referring to constant. So this is uniform motion, constant velocity. Okay, and so we're saying there an object is traveling at a constant speed. Which means if I look at a position versus time graph, you'll notice that x is on the vertical axis. That is the position, how far away it is from an origin or a reference point. And in every time increment, it's going the same distance in each of those time increments. Which means that the velocity is going to be constant. Maybe this velocity is at 5 meters per second, or that velocity could be at 28 meters per second. It doesn't matter, but it is a consistent, it is staying the same. All right? Next we have, let's take those away. Next we have an acceleration time graph. Now I want you to look at this acceleration versus time graph in comparison to the velocity time graph. The velocity is the same, it's constant, which means, is this object accelerating? No, it's not. It can't be accelerating. So the acceleration is 0. And you'll notice on the bottom here, the line is directly on that axis. So acceleration is equal to 0 meters per second squared. It is not accelerating, and that is very helpful. So for constant motion going at the same speed, you will have this straight line going up. For a velocity time graph, it's constant, so it's a horizontal line, and there is no acceleration. The next type of graphs. Here we've got motion with constant acceleration. Now an object is going faster and faster and faster and faster and faster and faster. It's going more and more quickly, which means that at the start, it won't be covering a big distance. The next increment, it's going faster. So it's going to be going further in that next second or that next 10 seconds or whatever the time increment is, it's going to have covered a greater distance. And the next time increment, it will have covered an even greater distance, because by then it's going even faster. Which means that if you come across to a position versus time graph, you are going to have this lovely curve where it starts slow and it's going faster, and so it's going higher and higher and higher up, but it's curved. It is not a straight line, and that is very helpful. Immediately, if I see a position time graph with a curve, I know the object is accelerating or decelerating for that matter. It is not going at the same speed all the time. It is covering different distances within each time increment. The velocity time graph. Now we said initially at the start, let's go halfway through here. At the start, it was going at a slow speed. Later on, the velocity or the speed was much higher. So it would make sense that now the velocity time graph is sloping up like that. It's going faster and faster because it's accelerating. And then the acceleration time graph is, there's acceleration versus time. is a specific value. It is not equal to 0. It has a specific value. But the acceleration time graph will always be a horizontal line, whether it's a positive horizontal line or 0 for that matter, or a negative horizontal line. Because by definition, we will only be tackling constant or uniform acceleration. So an object will either not be accelerating, which is those first 3 that we did, going at uniform motion, or it will be going at uniform acceleration. We will not deal with changing accelerations at high school level. So you're considering here a horizontal line for the acceleration. It could be a positive, as I've got here, or it could be that you've got, let's start with just an axis here. It could be that for your acceleration versus time measured in seconds, acceleration measured in meters per second squared, it could be that you've got a negative acceleration. And notice that is below the axes. So if 0 or 0 is there, it could be a negative value, maybe negative 9.8 for gravity. Okay? The idea behind this is that you can actually plot a negative on these axes, and that is fine as well, but it will always be a horizontal because we're not dealing with changing acceleration. It will be a constant or uniform acceleration. But you will often be required to draw graphs. And based on the description of motion in words or from a diagram. So I could give you a position time graph and ask you to draw a velocity time graph from that information. It's incredibly important that you can interpret between these. So, some useful definitions as we work through. I want you to make sure you've got those graphs in mind, but now I want to talk a bit more about what information we can gather from those graphs, what we can take out from those graphs. But I want to just remind you of some useful definitions we've done earlier. Last week we spoke about velocity, and specifically average velocity. And by average velocity we mean the displacement divided by the time taken. How far something has moved divided by how long it took to get there. And for average velocity, you can see this little v here, it would be change in position divided by change in time, or displacement divided by change in time. So that's a very useful equation to keep in mind. The next one, that was for velocity. The next one I've got is for acceleration. And acceleration is how quickly the speed or the velocity is changing. So if it's going faster and faster, it's accelerating. How much? Well, how much is it? What's its change in velocity divided by its change in time? And so we've got acceleration is change in velocity divided by change in time. I put those two equations in, I'm circling them because I want you to have that in the forefront of your mind, because the next thing I want to talk about is some tools that we're going to use as we work on graphs. Using graphs of motion. Notice we have the concept of gradient. Now the gradient means the slope of the graph. How steep the slope is. It could be a steep graph or it could be a shallow gradient. Steep versus shallow, it is the slope. When we work in gradient in maths, and I want you to make sure that you try not to compartmentalize, but use what you know in maths and what you can use in science, you use them together. So gradient, we're talking about the change in whatever's on the vertical axis divided by what's on the horizontal axis. Some teachers may speak about rise over run or something like that. The idea with that is you're looking at what is the change in the vertical axis divided by what is the change in the horizontal axis. That will give you the gradient. So, if you've got the gradient of a position versus time graph, then what is on the vertical axis is change in x. What is on the horizontal axis, that is going to be change in time. So, you then actually have delta x over delta t for the gradient. But hold on, what is change in x over change in time, or change in position over change in time? Hold on, that was the same thing as the velocity, because that was what our definition for velocity was. So looking at a position versus time graph, if you go and work out the gradient, you will get the velocity by definition. In the same way, if you've got a velocity versus time graph, the velocity is on the vertical axis, the time is on the horizontal axis, and so the vertical axis will be change in velocity over change in time, and the gradient will give you the acceleration, because by definition, acceleration is change in velocity over change in time. And so gradient can be an incredibly useful tool as you work with these position versus time, or accelerate, or velocity versus time graphs. The last one we need to consider is the area under the graph. And when I speak about area, we usually thinking length times breadth, because that would be for a rectangle. If you had a triangle, it would be half base times height. The area under a graph is going to give you, for if you've got a velocity time graph, it will give you the displacement. If you've got an acceleration versus time graph, it will give you the velocity. So incredibly, incredibly useful tools to work with as you go back and work with and gather information from a graph of motion. But you must make sure that you have in your mind what is on the axes, because whatever's on the axes will help you and will give you a lot more information, and you can work out if I've got the gradient or if I've got the area under the graph. When we come back from the short break, we're going to look into some questions. So go now and go and try that challenge question and make sure you get that one right. Katlego, over to you.
Thank you very much, Tracy. Of course, we're going to be giving you a beautiful, beautiful, beautiful Casio calculator and prices from ranging from Xperia, Sony Xperia phone, and airtime, sponsored by Vodacom. Just make sure that you follow the hashtag #GetConnected. And, you know, after the break, I'm going to be giving you more and more of what this competition entails. So stay tuned. Welcome back, Mindsetters. You're still with me, Katlego. The show is the show that you like the most, that is extremely productive. It's Mindset Learn Extra. And today we're doing Physical Sciences Grade 10. So get those notes and pens and everything that you're going to need to learn with us ready. I'm with Tracy in the studio. And of course, just go to our Facebook page. It's at www.facebook.com/Learn Extra, where you can access all the notes that we have for you. And of course, you can stand a chance to win great competitions if you just go to a Test Yourself portal, and that's where it will direct you. Test yourself as many as you can, and then you'll stand a chance to win this beautiful, beautiful Casio calculator, proudly sponsored by Casio. I'm going to be giving you information, of course, on an exciting competition that we've got in store for you. If you are intending on getting a driver's license soon, you better get it ready and get it going. And we've got a competition, of course. Sony Xperia is giving away a beautiful, beautiful cell phone and airtime, you know, ranging to up to 60 rands. So make sure that, you know, you get in store with us, and then you don't touch that dial, and then you will just make sure that you stand a chance to win those great prizes that we've got lined up in store for you. But right now, I'm going to hand it over to Tracy. Just take it away.
Thanks, Katlego. So Mindsetters, now we're going to tackle this question, and this question is going to ask us to draw a graph. So let's go with it. Car racing is very popular in South Africa. Many young people want to test the speed of their cars and meet regularly at racetracks. Now, fortunately, they're doing this on a racetrack and not on public roads, because as you can imagine, if you were driving a car and someone else is racing, can be very dangerous. An oval racetrack has a lap distance of 2,000 meters, so that's important. The car has to complete 5 laps. So there you've got this picture, and going around once is 2,000 meters. What distance will the car have covered at the end of the 5 laps? Well, if it's going around once, 2,000. Another time, 4,000, 6,000, 8,000, 10,000. So after 5 laps, it would be 5 times the 2,000 meters, and that's going to give us 10,000 meters, will be the distance that the car has covered. The next question asks us about displacement. And you might say to me, but Tracy, what is the difference between distance and displacement? Surely, if it's gone a certain distance, the displacement should be the same. Well, sometimes it is, but in this case, it's not. Why not? Well, because when it goes around the whole lap, it comes to a point where it has come back to its starting point. And that means that its displacement hasn't changed its position at all. No, it hasn't. Yes, it's gone a distance, but it's come back to the same place it started. And so it hasn't been displaced anywhere. It hasn't changed its position. So what will the displacement of the car be from the starting point after the 5 laps? It will be 0 meters. It hasn't moved at all. It's come back to its starting position. So yes, it might have, burnt up petrol and all of that, but it will not have been displaced anywhere. The next one asks us to use the data to draw a distance versus time graph for the motion of the car for the 5 laps. Now, I've noticed here that we actually don't have the data, but it's okay. I've got it on my notes, so we'll just work with that. Provide a suitable heading from your graph, and they've asked us to work with a distance versus time graph. So to start, I want to work with what kind of heading I would have, and I will fill in here. It could be the relationship between the distance covered and the time taken for the car. Now, I've started by filling in some values on my y-axis and on my x-axis. The vertical is the y-axis, and the x-axis is going to be the time, the horizontal axis. So you'll notice I've filled in some details because I know we don't have that long. So I've just gone and filled in those values. But always, it's incredibly important to fill in what are you working on. So that's going to be time in seconds. And on this side, these are the number of laps. So if you'll notice, that's going to be 2,000 laps, 4,000 laps, 2,000 meters, which would be 1 lap, 4,000, which would be 2 laps, 6,000, 3 laps, 8,000, 4 laps, 10,000, 5 laps. So this is going to be my distance covered. And that I'm measuring in meters. And I filled it in already. So the first, now I'm going to do these data points from memory. So hope they're going to be correct. It's incredibly important to fill in, and I think the first one was 55 seconds. So if that's 50, 60, 70, 80, 90, 100. So halfway through would be 55, and that was our first lap. So it's going to be, that's my first data point. The next lap was in 110 seconds. So it's going to be 110 would be there. So my next data point is going to be here. The next one was 165. So 150, 165, and it's going to be over there. The next data point would be, I think it was 175, so 275, which would be halfway through, so 250, 275, and that would be 800. So notice I'm filling in there. And the last one was, I think, 385. So 350, 360, 70, 80, 85. And I'm plotting that one, I think. Should be over there. Hold on. Let's just clear that nicely and do this one nicely up to there. Okay. Now, you'll notice that this graph has got two different sections to it. What the instructions were actually asking was for us to join the dots, because we're not looking at an overall trend in terms of, very often we would plot a graph and we would actually just look for a line of best fit. But here, that would be one set, and let's try and draw that slightly more neatly. That's slightly better. And then notice that the line, the car is actually going slower here. So it's got two different slopes to this graph. And that's very helpful because it's telling me lots of amazing information. It says to me at the start it's going quickly, and then towards the end it's going slowly. How do I know that? Well, I'm looking at the gradient of this graph. The gradient is initially steep and then it levels off. And that can be very, very useful. So, the next one, use your graph to determine how long the car took to complete 2.2 laps. Well, 2.2 laps, let's work out the distance. That would be 2.2 laps. Each lap was 2,000 meters. So, 2.2 multiplied by 2,000 is going to give me 4,400 meters. Now I want to go back to my graph and I want to go and find where's 4,400 meters on this graph. So I'm actually going to take a different color and I'm going to read off, well, this would be 4,000. Halfway through there's 5,000. So 2,000, 4,200, 4,400, 600, 800, 5,000. So it's going to be at that point over there. And what I would need to do is take a dotted line across and actually show where is it cutting at that point. It's cutting there, so now I'm going to dot it down and find out where the time would be. It's going to be 100, 110, 120. So 120 seconds is my answer. And I've shown it on the graph by indicating this highlighted line that I've got. I'm reading across and down. If it was a time, I would read from the time up and across. And that can be very helpful because you want to be able to take information from a graph. That is why we draw graphs. So I could ask you, how far had he traveled after 350 seconds? Well, you would go, all right, 350 across and read across like that. But you need to be indicating that. So take a highlighter or a different color pen or something and make sure you mark it on the graph. The next one. So we've done that. Calculate the speed of the car during the first 100 seconds. So we've got 100 seconds there, and I want to actually just come along here and say, okay, I'm looking at this point, and I'm looking at that initial part. So for the first 100 seconds, well, it would be helpful. What am I going to do? I'm going to need to work out the gradient of that line, the gradient of that slope. And so if you'll notice, I'm going to work between 0 and 100, and we can go from there. So, make sure we've got some space. I think I'm going to need to give myself some space. So, gradient. And gradient is change in y over the change in x. And in this case, the vertical is change in the position divided by change in time, which is the velocity. Let's just write it here, velocity. Now, if I've got change in the vertical, what was the vertical? I will need to go and read that off. And it was 3,000, so 2,000 to 22, sorry, 2,200, 2,400, 600, 800, 3,000, 3,200, 400, 600. So it would be 3,600 minus 0, because I'm working with from that point up there, that's my 1 point, and my second point is going to be 0, because that's just the easiest. If you can work to 0, use that as a point. Doesn't matter which points you use, but as long as you are working with that same straight line, it doesn't really matter which points you choose. But I think the easiest will be, they asked us for 100 seconds, so let's work with 100, and we can very quickly work off that line and work with that. So it's going to be, the change in my vertical was 3,600 minus 0, and it's 100 minus 0, and that's going to be, on my calculator, 3600 minus 0, which I know is fine, divided by 100 equals 36. So it's 36, and my units, meters per second. Now, next question. We've done that one. Draw a sketch graph of the speed of the car versus the time for the 5 laps. All right, now I want us to go back and look here that the graph actually changes. For the first 3 laps, it's going at a specific speed. For the next 2 laps, it's going a lot slower, and that gradient has changed. So it would be useful to go and find out what the gradient is at this point here. But they did only ask us for a sketch graph. So we could go and work out the gradient again. You know, we could maybe choose those 2 points. That would be fine. And we certainly could go and do that for that triangle. But knowing that I don't have that long, I'm going to just do a sketch graph. And so I start with time is in seconds. And they've asked me for velocity versus time, velocity in meters per second. I want to note that the velocity initially was 1's velocity, and then it slowed down. So I'm not putting any numbers on the graph, but I'm drawing a horizontal line. That is for the first 3 laps. And then, let's just make this more of a dotted line. The velocity changes, and it's a different velocity. And that's quite useful to note. I could go and write in that this value here was 36. I worked that out. And this other value would, I know, be lower than 36. I haven't worked it out what it actually is, but I know in terms of the sketch, I could go and work it out. In terms of the sketch graph, it's not necessarily necessary. Depends on what they ask in the question. But they didn't indicate that I needed to write in the values. So for now, I'm just going to do it as a sketch here. Helpful to identify that what we have done is worked out the gradient of that graph for the first 3 laps, and then we could work out the gradient over there. And this is a position versus time graph, so the gradient will give you the velocity of that graph. Very, very, very useful to work with. when we come back from the short break, we're going to work on the challenge question. So I want you to make sure that you've answered that challenge question and that you have really, really put on your thinking caps and answered and thought through all those things, because I don't want to just answer it and give you the answers. I want you to think about it and prove to yourself that you can do this. So Katlego, over to you.
Indeed, Tracy. Just go to our Facebook page. It's at more or less Learn Extra. www.facebook.com/Learn Extra for that challenge question so that you can interact with Tracy. Just make sure that you throw all the questions that you have regarding what we are learning today, and we'll make sure that before the end of this show, we have answered you. Just go to our Facebook page still again for you to go to a test yourself portal and more or less answer the questions there, and you stand a chance to win a beautiful Casio calculator, proudly sponsored by Casio. When you come back, as I told you, we've got an abundance of competitions. I'm going to be giving you information of the new competition that Mindset Learn Extra is launching on the 15th of September. So if you are an exciting or more or less a budding driver, just make sure that you tune in, and we'll make sure that we give you information on that. Just in the meantime, just stay tuned. Welcome back, Mindsetters. And one of the greatest things about being 16 or over 16 is that you're becoming a responsible being, and that includes you actually having to go get your driver's license. So if you are over 16 or 16, and more or less I'm going to be giving you, the grade 11s and grade 12s, more information on this when time goes by. But if you are 16 or over 16, just make sure that you keep tuned to Mindset TV, and we're going to be introducing a new exciting competition on the 15th of September, where more or less you can be sure that you're on the right track in terms of you getting your license. And of course, our notes are up right now as we speak, so just make sure that you go there and then you click the Test Yourself portal, and just make sure that you test yourself as much as you can, and the one with more or less enough or right answers stand a chance to win a beautiful Casio calculator sponsored by Casio. And we'll be introducing, or we'll be announcing, the winner of the Casio calculator for grade 10 when the show ends. But then right now, I'm going to be heading over to Tracy to just more or less give us more of what Physical Sciences has in store for us.
Fabulous. And Mindset is, those of you who are starting to get excited about learning to drive, you really need to make sure that you've got all this understanding about motion, because it's really important that you are safe on the road and that others are safe on the road around you. So do make sure that you understand some of the implications of driving and learning to drive. And do stay tuned. That sounds like a very exciting competition coming up. So Mindset is, the challenge question was about a man running. Very often we've got a car driving, so make sure that you've got that driver's license and learner's license on the way. A man runs from point A in a straight line along the track, and the points given are A, B, C, D, E, F, G. The velocity time graph below represents the motion of the man. So here we've got a graph that we are representing his motion. And I want us to start by talking through what can we see immediately from the graph in terms of what is happening during this motion. So I'm going to write a bit of a list here to start by interpreting. So between point A to point B, and then B all the way through to point E to point G. Okay? Notice it's a straight track that he's running on. From point A to point B, what does the graph tell me? Remember, it's a velocity versus time graph. So what does that tell me? The graph is an increasing slope like that, which means the gradient is a positive gradient. And that is an indication to me that for the first part, he is accelerating. How do I know that? Because the velocity time graph had a positive gradient over here. Then from B, C, D, all the way to E, the velocity was a constant velocity at 2.5 meters per second. So the first part he was accelerating, here he's going at constant velocity. and that was at 2.5 meters per second. And then between point E and G, he must be slowing down, because if you think about it, by the end here, he gets back to 0. So he is slowing down in those last 40 seconds. He is going back down to 0 in terms of his speed or velocity, so that means he must be decelerating. So we'll jot that down, decelerating. And I want you to note that it is a negative gradient. The slope is like that. And if you think about it, in maths, when you do gradients, and if you've got a line that is a horizontal, that is a slope that is slanting in that direction, you would say that that's going to be a negative gradient. And in the same way here, we're going to interpret that this is going to be decelerating because of that negative. So I can say here, it's going to be a negative acceleration. Okay. Now I've interpreted what's happening. I can start to answer the questions. Using information on the graph, calculate the acceleration of the man, not through the whole thing, but specifically from E to G. And I'm going to look here and say, okay, he's decelerating. How am I going to work out the acceleration, or in this case, the deceleration? It's going to be using the gradient of this graph. So, from E to G, E to G, we're going to work out the gradient. And the gradient is change in the vertical divided by change in the horizontal, which is change in the vertical. It ends at 0. So it's final minus initial, which means 0 minus 2.5 divided by minus 2.5 divided by the horizontal. And it's final, which is 100 minus 60. Okay, so we've got some values that we're going to plot on this graph, that we're going to plug into our calculator. Let's clear those. It's going to be negative 2.5 divided by, open brackets, 100 minus 60, close brackets, equals, and get it as a decimal. Negative 0.0625. So negative 0.0625 meters per second squared. Now I actually don't want to leave my answer as a negative. I want to write here 0.0625 meters per second squared, but with a specific direction. Did the question tell us what the direction was that he was running? It just said he's running along a straight line. It didn't say north, south, east, west, so I must give my answer here opposite to motion. Notice I'm actually interpreting what that negative meant. I don't leave my answer with a negative, I'm interpreting what it means. And that's very valuable. The next question, the distance covered by the man. Okay, now if you're going to speak about the distance covered, we want to talk about the area under the graph. And if you'll look at that, we've got a number of different shapes we could work with here. We've got a shape here, that's a nice little triangle we could work with. We've got, let's work with this rectangle there. And last one, let's go with blue. We can work with this triangle over there. So I've got 3 different shapes that I can calculate in terms of the area under the graph, and I'll just take those three and add them up. And that's probably the easiest. If you want to, you can go and work out the area of a trapezium or some other shape and certainly go and add them up or whatever. I find these probably the easiest for me. So that's going to be my number 1, that's going to be my number 2, and that's going to be my number 3. Okay? So I'm going to do this in 3 stages. So for stage 1, this is area under the graph. We're looking at, for number 1, it's a triangle. So it's going to be half base times height. And the base is 0 to 25, and the height is going up to 2.5. So that is equal to half, give ourselves some more space, 25 multiplied by 2.5. And we can work that out. 0.5 times 25 times 2.5 equals 31.25. 31.25 meters. Next one. This is the rectangle. So from B to E, and it's going to be stage 2. It is length times breadth. The length was, well, now I'm going to need it to work it out. It's going up to 60, but it's only started at 25. So 60 minus 25, and the height there was still 2.5. So let's go and work out. 60 minus 25 was only was 35. So this is 35 multiplied by 2.5, and so 35 multiplied by 2.5 is equal to 87.5. That's the distance it covered in the second stage. The last one, stage 3, was also a triangle. So half base times height is going to be half. What is this? 60 to 100, which is, I know, 40. So 40 multiplied by 2.5. Back to my calculator. 0.5 multiplied by 40 multiplied by 2.5 is equal to 50. So we've got here now, to answer this question finally, I have to add up each of them. 87.5, I think it was, plus 50 meters. Each of those, let's just check them. That looks right. And so the total distance covered was 31.25 plus 87.5 plus 50 is equal to 168.75. 168.75 meters was the total distance covered. And that's very helpful as we work through each of these. Let's just write that more neatly. 0.75. As you work through these, it's incredibly important that you can interpret what is happening on this on these graphs of motion and work out, when do I need to use area under the graph? When do I need to use the gradient? Each of these can be incredibly valuable, but you need to be able to interpret what is happening on these graphs. So mindsetters, I hope that's really helped you. I hope you've got your thinking caps on and that you're going to be working on these really, really well and that you can be able to interpret graphs really well. So from me, Tracy, I'm signing off for now. Keep well, God bless, and I'll see you next time. Thanks, Katlego.
Thank you very much, Tracy. And grade 10, I hope that was really, really beneficial. Just make sure that you get in touch with us on Facebook. Go there, test yourself. And of course, just before we wrap things up, I just had to announce the winner of our Casio calculator. Congratulations, of course, to Teddy Moloto. You are our winner of a Casio calculator. So to be like Teddy, just make sure that you go on our Facebook page, go there and then go to our Facebook site, go to notes, test yourself, and make sure that you stand a chance to win this beautiful Casio calculator. And of course, it's been a pleasure being in your presence and in your midst. And physical science is always an exciting subject indeed. So make sure that you go there, do me and Tracy, and of course, the mindsetters are proud in that exam room by nailing it. And of course, I must make sure that I remind you that the learning never stop. I like a quote from Mahatma Gandhi, which says that you have to live as if you were to die tomorrow and learn as if you were to live forever. That with that note, you have to make sure that you keep it in mind at all times that the learning never stops. So take care and keep well. And from me, Katlego, we'll see you again. Keep blessed.